So our next presentation is from Tom Bone. After working in industry for 2 decades, Tom decided to go back to graduate school in the Space Propulsion and Power Laboratory at the University of Maryland under the direction of Ray Sedgwick. And he's working on direct power extraction from fusion. So over to you, Tom.
Very much. Appreciate it. Hello, everyone. Thank you for attending my presentation. That was an awesome presentation beforehand. I somewhat regret I have to follow it. But this is also my first conference presentation, so go easy on me. As you just heard, my name is Tom Bone. I am a first-year graduate student at the University of Maryland, working under Dr. Raymond Sedgwick. Jerry Carson, who you heard from yesterday, is a colleague of mine, and my work parallels his work and uses the same system design in general. So just to start with, I'm going to review that for those of you who either were not here yesterday afternoon or just so you can sort of picture along what the fusion system, this direct fusion drive system looks like. The blue area that you can see there is the reactor, and the gray squares with the X in them are the toroidal high-temperature superconducting magnets that create the magnetic mirror. This is an axisymmetric view, so you just sort of twist it around the center line, and that is the full system. Now, the red dots are the actual fusion fuel, and the gray line between them, along with the black lines at the edge of the reactor, are the anode and the cathode that supply the radial electric field. The radial electric field works in conjunction with what's essentially a axial magnetic field at the center to create that azimuthal rotational velocity for the additional confinement of the fusion fuel to allow that fusion to occur. Now, once that fusion does occur, the alpha is produced. One of three things happens. They either stay in the reactor and help to energize the fuel, or they escape through the left-hand magnet towards the power conversion side and get recycled back through as electricity, or they go through the right-hand mirror out the back, where they get mixed with a warm plasma and used for thrust. So that's the general overview of the system itself. Now, one of the big considerations for how this system would be designed has to do with what the fusion fuel is that's being used. Jerry's work has mostly focused on DT at this point, and these are by far not all of the possible fusion fuel combinations. However, it does show the sort of concerns that you think about with this. There are those that produce neutrons like DT and DD. There are those that do not, D-helium-3, although there is a side reaction that does produce some neutrons, and PB11. PB11, for those of you who aren't familiar with it, is hydrogen and boron, the hydrogen being ionized, just a proton. And that also demonstrates another difference. There are some elements here that are rare, like helium-3 and tritium, and others that are more abundant, like deuterium, hydrogen, boron, etc. Now, my focus in my research is on PB11. And PB11 has some distinct advantages and some distinct disadvantages as well. The advantages, as I said, it's aneutronic. It only produces charged particles, and those charged particles can be confined. The neutrons are particularly difficult because they aren't able to be confined by magnetic or electric fields and therefore do damage wherever they go. It's also abundant, as I said. But the disadvantages are also very distinct. It's much more difficult. You need much higher temperatures, whereas DT tends to fuse around 10 kiloelectron volts. PB11 doesn't fuse until at least 130 kiloelectron volts and generally a lot higher, depending on exactly your needs. But the biggest disadvantage with using PV11 is something called Bremsstrahlung Radiation, which is generally produced in approximately the same magnitude as the actual charged particles. And so what is Bremsstrahlung radiation? Well, it's a impact that happens when electrons are deflected by a nucleus and produce photons in the X-ray range. And this is a particular problem with PB11 because boron has 5 electrons, and at this temperature is fully ionized, so you have a lot of electrons moving around this fusion plasma, creating this additional radiation. So in order to make this a viable fusion fuel option, a significant portion of that Bremsstrahlung needs to be captured in some way, turned into heat, and then converted into electricity. And this is sort of a cartoonish little version of what that might look like. Again, an axisymmetric view with the blue on the sides being the magnets and the yellow slatted object being some sort of outside structure that is absorbing the heat from the Bremsstrahlung radiation. And again, it's axisymmetric here. And in order to convert that heat, there are many ways that you could do it. You could use mechanical heat engines, but those come with their own disadvantages, like they generally need to be fairly large to be efficient. There's moving parts. You don't have a lot of maintenance ability in space. So oftentimes in space applications, you're using a direct thermal to electric type of device, such as a thermovoltaic or a thermoelectric. Sometimes thermionic, although that has not been used very often. Thermionic energy has been something that was used by the Soviets in the, I believe in the 70s and 80s a couple of times, but in recent decades has gotten a lot more interest. And I'll go over a little bit more about thermionics in a moment. That is what I have focused on in my research to convert this Bremsstrahlung. And why? Because we're in space, we want something that's low maintenance, and this has thermionic energy converters don't have any moving parts. They use electrons as their working fluid. They're low mass. They can be made very small, but very importantly, they're good at high temperatures. And we've got all of the heat that you need with millions of degrees Kelvin in the reactor. And because they work at a high temperature, and because they don't have a lot of moving parts, there is a very high potential efficiency for them. So how does a thermionic energy converter work? As I said, electrons are the working fluid of this. It's essentially a thermionic emission is when a piece of material is heated up to the point where the electrons overcome the barrier to escape the material entirely and essentially boil off. That characteristic is called the work function of a material. The work function of the material is simply the amount of energy it takes to remove the electron entirely from that material. And that work function, along with the temperatures of the material, are the important characteristics of a TEC. And so in the, again, little cartoonish diagram here, where it says Pn, that's the energy coming from the reactor, the Bremsstrahlung, incident on a material called the emitter. And that emitter absorbs the heat, and you coat it with something or make it in such a way that preferentially one side of it has a low work function, and the electrons that have the energy to escape towards another piece of material called the collector. And if those materials are close enough together, the collector has a lower temperature and a smaller work function. The electrons will migrate to that and flow through the leads to a load of some sort, creating a circuit. And so now there's other obvious heat transfer mechanisms going on here as well. Because the emitter is generally very hot, there's also radiation, blackbody radiation. There's some material that has to separate these two layers of material that you'll have some parasitic conduction for, as well as some back current as well from the collector to the emitter. Most of that I have neglected in my particular look at this to keep it a little bit more simple and just to focus on the major energy losses, which are the losses through the electron and through radiation. But one of the other big issues with thermionic energy converters is something called space charge. Now, when the electrons flow off of the emitter towards the collector, sometimes they build up in that interelectrode space, creating an additional potential barrier for the electrons that are trying to move off of the emitter. And so as the space charge builds up, the current from the emitter starts to go down. And these are generally, this issue is generally fixed in one of two ways, or attempted to be fixed in one of two ways, by two different types of TECs, one that's called a vacuum TEC. And in a vacuum TEC, you're simply pumping out all of the air between the two and putting the emitter and the collector as close together as possible. Unfortunately, in order to do this, generally it's been found that it has to be within a few microns of each other, if not a few hundred nanometers, which is a definite engineering challenge. The other way that it's been taken care of in the past as well is by using something called a vapor TEC, where you put an positively ionized vapor in between the emitter and the collector, which helps transport those electrons and mitigate that space charge issue. Now, this diagram here just takes you through the power flow of this system, and that's why I wanted you to have that mental image of what the system actually looks like. I'll start here with the green radial electric current arrow. So that's the cathode that's creating the electric field that is helping to guide the azimuthal rotation of the plasma. And that creates that angular momentum. And that angular momentum is dissipated in a couple of ways. It can be dissipated through boundary losses. You'll lose some of the fuel through the mirrors and some perpendicularly. But you'll also lose some of the angular momentum through viscous losses as the plasma shears as it rotates. And that energizes the plasma. That actually heats the plasma. You also get some heating of the plasma through the actual fusion process itself. Some of the alphas that are created are going to thermalize in the reactor and create the energy that's needed to continue that reaction. Otherwise, that energy also is dissipated in a few different ways through boundary losses again. And in this case, we're going to continue consider any of the alphas that go towards the right side and into the thrust chamber as being boundary losses, as they're not getting recycled back through the system. But other than that, the alphas that go through the left side of the mirror get changed into a electric current through the SW deck. The radiation losses get changed into some sort of electrical current through the TECs. And although there are some unconverted losses, anything that is converted goes back through a high voltage conversion and cycled back through the cathode to create that electrical current to keep the process going. So in my particular research, and I'm just going to go through it pretty high level here. There's a paper that gives all the gory details if you so wish. But the idea is to create an analytical model, just looking at the ideal conditions of using a TEC to convert, or a group of TECs to convert a PB11 fusion that is producing this Bremsstrahlung and be able to sustain it. Determine what the lowest amount of Bremsstrahlung production could be for a given reactor power, and find the parameters of the TEC, the parameters being the temperatures and the work functions of those TECs that would create a power balance that works for this particular system, along with what the efficiencies of those are, and then figure out what the electric and magnetic field strengths are going to be necessary to combine a plasma like this. So the research began by looking at what kind of power was going to be needed by the spacecraft. And as Jerry talked about yesterday, the guiding principle for the work we've been doing is that we want to create something in the range of 200 kilowatts to 1 megawatt of jet power from the propulsion system, which, assuming the lower end of that, means that we're probably going to need at least a 1 megawatt reactor power to be produced in order to produce that amount of jet power. So that's what was assumed to start with. And from that, the rest of the assumptions flowed. And on the right-hand side here, you see a number of the initial values that were looked at. Specifically, I'll point to the emitter temperature, the collector temperature, and the emitter and collector work function, because those are the four characteristics that determine the amount of current, the amount of power, the efficiency of a particular TEC. And the values that I looked at were all values that were generally tested in the literature by a number of folks over these past few decades. Now, the first thing that I tried to look at then, if we have 1 megawatt of reactor power coming, on the bottom left, you'll see a plot of the difference between different ratios of protons to boron in the fusion fuel. One being a equal ratio up to 9 times the amount of protons as boron. And as you can see, as the ratio increases, the Bremsstrahlung radiation, which is the curves, are coming down to where they're almost exactly equal to the thick blue curve, which is the reactor power. Now, that makes some sense because Bremsstrahlung is created by all of those electrons. And so since boron has 5 electrons, by raising the amount of hydrogen in the concentration, the average number of electrons in the fusion plasma go down. But it does look like the return becomes much lower as soon as you get to 5, 7, 9 times the amount of hydrogen to boron. Now, from this, once we have figured out that the amount of Bremsstrahlung created by this amount of fusion power is approximately the same as the amount of fusion power, we can use that to create a power balance of the power coming into the emitter of a TEC, and then just looking at the electron and radiative heat losses from the emitter and balancing that out. And so on the right, you see plots of the current density and power densities created by some of the better combinations that worked for this power balance. Option number one was by far the best, on the order of 10 to the 4th watts per meter squared and 10 to the 4th amps per meter squared, since the voltage is on the order of 1 here. And this is, and as you can see on the bottom, that that table shows what the temperature and work functions were for those particular options, 1 and 3 being the 2 best out of those 5. And as you can see, the temperatures, the emitter temperature, the collector temperatures are pretty high, although they can still go quite a bit higher with the amount of energy that's coming off that fusion plasma. And specifically for option 1, you can see that the emitter and collector temperature are considerably different, which leads to the efficiency of these. Looked at both the Carnot efficiency, which is simply the ratio of the collector temperature to the emitter temperature, essentially, and what's called the electronic efficiency. And the electronic efficiency is just a measure of the ideal electron transport that the TEC can provide. And so this is the, under these ideal conditions, this is essentially the best possible conversion efficiency that this TEC could provide. So option 1 had a Carnot efficiency of just about 40%, significantly higher than the second best, which was just under 20%, with an electronic efficiency of 36 or 37%, so not too much lower than the Carnot efficiency. And then the final thing that I wanted to look at was what are the confinement fields that are necessary to confine this plasma. And this is based on a lot of the work that Jerry Carson did and talked about yesterday. Start with finding out that the Mach number of this rotation needs to be around 5 to 6 in order to confine the plasma. And from that, you can find the plasma's beta. And beta is a non-dimensional number that just is the ratio of the plasma pressure to the magnetic pressure. And from that, you can calculate the magnetic and electric fields. And so from the figures that Jerry got for his research, it looked like that the beta would have to be somewhere around 0.17, which creates an electric field in the range of 300 megavolts per meter being necessary, and the magnetic field being about 16.6 Tesla, which is a very high number. In fact, it's a little worse than that in some ways, because how a magnetic mirror works is that the mirror ratio is what helps determine the confinement. And the mirror ratio is the magnetic field at the midplane compared to the magnetic field at the actual mirror, the magnetic mirrors themselves. So this is the magnetic field needed at the midplane. So the mirror ratio is likely somewhere around 2, maybe a little more, maybe a little less, but we're talking really somewhere in the range of 30 Tesla being needed, which is something that not very many places on Earth can provide right now. So in summary, there are a few things that my research was able to see, which is one, that the hydrogen-rich fuel is beneficial, although that the beneficialness of it reduces as you get to a higher ratio. It was able to find a combination of TEC parameters that does create a pretty high power density of 10 to the 4th watts per meter squared. And given that the reactor size here we're talking is on the order of 10 to the 5th, it's at least giving a possible conversion percentage somewhere around 10% in these very ideal conditions. But the necessary magnetic and electric field strengths are high and maybe not particularly practical, at least at this particular point. But there is a lot more work to be done here. This is very preliminary and very, sort of surface level. Certainly, there could be a much more optimal ratio of hydrogen to boron, and there may be some things that have to be kept in mind, like if the ratios are not even, losses may not be equal between the two species. There may be some other combinations of TEC parameters. My research really was looking at a pretty brute force method of trying to find the ones that met the power balance. But there are others that could be better. And there's also a need to take space charge and other loss mechanisms into account, which I did not. But I think the most important thing to continue this research and make this a viable fusion fuel is to find additional ways to limit those confinement fields as much as possible and bring down the needed electric fields and magnetic fields that would be needed to produce this amount of fusion. So just really quickly, I want to thank NASA and the A. James Clark Foundation, both of who helped provide some of the funding for my research over this past year, as well as my fellow members of the Space Power and Propulsion Lab, especially Jerry Carson, who very much helped me out with a lot of the numbers for my particular presentation here. So, questions?
Interesting presentation.
Thank you.
What kind of materials are you looking at for the thermionic converter?
Well, I mean, most of the research done on thermionic converters uses some sort of refractory metals like niobium or molybdenum. Yeah, right. Tungsten. But there's a lot of different research out there regarding, especially, so one of the big things is that on you need both the emitter and the collector to have low work functions, but you need the collector's work function to be much lower than the emitter's work function. So the real question is how low you can get the collector's work function. There's been a lot of work done on diamond doped collectors that produce like a very low, like 0.5 electron volt collector material. But I don't think I've looked at some of those materials, but a lot of the work that I've done so far has sort of discounted the individual materials. That would be the next step, though, is trying to look at specific materials. And the biggest deal here is that we're working at such high temperatures. You need something that can accept all of this heat and not melt or not, have other bad effects because of it. So,
question on the gain, especially when talking about, and I'm talking scientific fusion gain here.
Yeah.
You guys looked into what your maximum possible is in an idealized case, because that's the hard bound. And specifically, have you looked into that as you increase the hydrogen ratio? Although it helps with Bremsstrahlung, you're paying to heat fuel that does nothing.
That's what I was saying at the end really needed to be looked at more. I did not focus too much on the actual fusion process of PB11 and focus more on its production of Bremsstrahlung at this point. But yes, I completely agree that definitely needs to be looked at much more closely, because there are a number of effects that you could have by increasing that amount of hydrogen. The hydrogen also did have the increased hydrogen actually did have some other beneficial effects. The Mach and beta numbers that were necessary got much lower when you increase the percentage of hydrogen in there. So, but there's some trade study that needs to be done there as to what the perfect balance is.
I'm not to pile on, but the it's a well-known result that if you don't do something about the Bremsstrahlung, you can't make PB11 go.
Right.
Because the losses are more than the power that you're getting out.
Right.
And while I love the work, and you'll hear me more on thermionics, go, but
yeah.
the intercepting only 10% of that power and then getting some fraction of that 10% to get back into the fusion isn't shifting the balance very much.
Right. Well, the 10% was the overall system, looking at the overall system of efficiency. The actual efficiency of the TEC, the ideal efficiency, was more in the 36% range. Oh, okay.
But in order to make the PP11 reaction light, you have to get a meaningful fraction of the Bremsstrahlung radiated somehow to get back into the fusion plasma, and that's a spooky process.
Yes. I mean, I think that coming into this research, my knowledge of this whole thing was very low. But coming out of the research, I think my first impression is this is a very difficult engineering challenge. There is absolutely no doubt about it. I don't know whether it's an impossible engineering challenge at this point. I mean, it certainly seems like it's not a near-term sort of thing. Like, the technology will have to improve in a number of different areas in order to make this feasible. But I think it's also worthwhile work to do to look at what it would need to be to make it feasible.
Cool. Maybe two questions, because I keep hearing thermionic and thermoelectric being thrown around. You guys are using a thermoelectric conversion process of thermionic?
This is thermionic. So gotcha. The difference, and I'm not a particular...
No, I guess I just heard TEC and then TIC being thrown around, so I guess wanted to clarify that.
If I said anything other than TEC, I apologize. That's all I meant.
Gotcha.
So.
Have you guys looked at combining the two together? I know there were some papers about if you take like the hot end of your thermionic emitter and then combining it with like the cold side of
I have read some about that. I've been more interested in reading some of the stuff about combining it with thermovoltaics, because there is a lot of radiation that's coming off of this because it's being heated so high. And there's been some good work on combining a thermionic process with some sort of solar collector sort of thing to help increase the efficiency, and it actually looks pretty good as far as the amount of additional efficiency that you get from it. So I think that would definitely be something that I would like to take a further look at.
Yeah, that makes sense, because if you can couple both processes, then you can, I guess, give yourself extra efficiency from just one stick into one.
Exactly.
So, yeah.
Exactly. Cool. So it's definitely, there's a lot of good research being done out there on that right now.
Okay, let's thank Tom again.
Thank you.